Okay, so our next speaker is Professor Justin Solomon from MIT. So the topic is linking the theory and practice of optimal transport. Let's welcome Justin.
Hi folks, it's a pleasure to be here today. I should apologize a little bit. I've been diagnosed with a vocal cord issue, and I just got off a flight from Russia, so it's going to be a little bit of a challenge, but bear with me, and if you can't hear anything, just let me know and I'll repeat. But in any event, I'm really glad to be here today and to share some of the research that's going on in my group at the other school, not so far away, Cambridge here, specifically in the area of optimal transport. I've had the pleasure of meeting many of you. I come from a group that does a lot of kind of diverse research in the geometry area. And of course, it would be my pleasure to talk to you guys about problems we have, not just in machine learning, but also in some other areas like computer graphics and optimization and some other places. But today, I'm going to tell you about sort of a line of research that we had specifically in an area that's sort of the intersection of probability, geometry, and large-scale optimization, which is known as optimal transport. Optimal transport has a very long, distinguished history. I'm sure I've left people's names out, and of course it's led to Fields Medals, Nobel Prizes, and now a French political position in the parliament there. But as a mathematical theory, it's sort of a geometric way to compare probability measures. And let's add a little bit of detail about what we mean. And the previous talk, actually, it's really convenient that it sort of set me up nicely for some sort of talking about transport as an interesting alternative, at least in one particular space of problems. Oh, time's up. Okay. Right. So here is sort of the typical pipeline that we have in the computational world for comparing functions or probability measures. Here it's just in one dimension. So I'm thinking of probability like a Gaussian distribution. So height is probability and the x-axis is location. And let's say I want to compare these. I just want to know how similar they are. So certainly many previous divergences fall into this category. One way that I can do it is I can take my two functions, p1, p2, subtract the two, and integrate. I think this is something we've all seen in some form or another. And of course, you know, the typical way we think about this is you subtract, square, and integrate, but these are probability measures, so maybe I really shouldn't be doing that, but things like KL divergence, L1 distances, and so on, all have a very similar structure, right? I iterate over the x-axis here, and I compare the different values. And if you take most measures of distance that kind of look like this, these are all over the place, statistics, probability, and so on, they have kind of a funny property, which is, let's say that I have two Gaussian distributions, two bell curves. And I take the bell curve on the right, and I just keep moving it farther and farther along the x-axis. And I plot the distance value that I compute from one to the other. The question is, what do I get? Well, unfortunately, what I don't get is that distance is proportional to the distance along the x-axis. Instead, what you get is that for a while it kind of looks like it might be, and then it just levels off and asymptotes. And the reason is that what these distances are measuring is not anything geometric. They're actually unaware of the x-axis here, but rather they're just measuring the overlap of these two distributions. And so for a lot of applications in probability and machine learning, the distributions that we have are associated with the piece of geometry, in this case just the x-axis. And in those applications, it may make more sense to actually have a theory that's somehow aware of displacement rather than just the vertical difference. So many of you, in fact I know some of you are familiar with the theory of optimal transport, but I'll give you this sort of 5-minute highlight version in case you're not. I know many of you are from out of town, but something you might know about Boston is that typically it's not this beautiful weather out here. This is a photograph of my front yard a few months back. And of course, as a lazy mathematician, you know, the city of Somerville won't allow me to go to work until I remove all of this snow from the path across the front of my house. This was actually a school day, which was really irritating. But I digress. And so, of course, there are many different ways that I could do that, right? I could scoop up the snow, walk to MIT and drop it there. Or I could do something more efficient, right? I could scoop up the snow and just drop it on the side of the street. But there's some minimum amount of work that I have to do to displace that snow from its current position to where it's going to go. Right? It's not zero work, there's a positive amount. And that is a property of the snow. It's not a property of my back or my shovel. Right? And that is exactly going to be the construction that we have in the world of optimal transport. It's sort of the minimum amount of work that it takes to displace mass to a new configuration. So let's formalize that a little. So let's say that I have rho 0 is the height of the snow in its current configuration. Rho 1 is where I want it to go. And now I'm a mathematician, so I want to plan very carefully how I scoop up my snow and drop it back down. And so my unknown variable here is a function pi of xy, which is the amount of stuff that I pick up at x and drop off at y. And there are a few constraints. Right? For one, I can't pick up a negative amount of snow. When I integrate over all y, this is like saying all of the snow at x integrated over all of the possible targets. What should I get? Well, I should get the total amount of snow that starts out at x. And similarly, when I flip the roles, I should get how much ends up at y. And any function that satisfies these three constraints is called a transport plan. If you kind of do your back of the envelope calculation, you might notice there's a linear number of constraints and a quadratic number of unknowns. So this is a big set. There are a lot of things that satisfy these constraints. So, in optimal transport, the basic thing that we do is we solve an optimization problem. Namely, we ask for what is the minimum over all possible transport plans. I'm sorry, I'm noticing that I've shifted notation. This is like rho 0, rho 1, previous slide. Over all the possible transport plans, I want to minimize work measured as distance times mass. And a typical kind of sleight of hand that happens in this literature here is that we'll generalize slightly and penalize distance to the pth power.
There's some requirement for the volume preserving sense, no?
In some sense, this is volume preserving by definition, right? Like it's picking up everything in you and dropping it all in you. Because these are probability measures, they have this.
Well, those are predetermined, prefixed.
Yeah, exactly. So the input is two measures, and the output is a distance and a transport. It's a great question. And of course, you could put a general cost here. That would be something called the Kantorovich problem. The most common one that we encounter in applications is specifically where there's a distance as your cost. And actually, for kind of funny historical reasons, this is typically known as the Wasserstein Distance. Named after, I always thought, like, oh, Maj, Kantorovich, Ampere, Wasserstein. It turns out he's a professor at Penn State, and sort of a historical accident that his name is here. But in any event, we have this terminology now. And the kind of nice thing is that what the Wasserstein distance does is it takes a distance on my base domain and it lifts it to a distance between probability measures. Right? And in fact, you can kind of double check that. So for instance, if mu and nu are both Dirac delta functions, so they're like secretly encoding one point, then this value is precisely the distance between these two points. Sort of generalized.
One question about notation. Why do we leave the 2p in that notation?
Oh, okay, this is really the pth power of the Wasserstein distance. So you need to take the pth root for this thing to have a triangular equation.
So we just need one. So we don't need another p.
Oh, yeah. So this is the p Wasserstein distance to the pth power. Yeah, sorry. I know it's kind of tricky to press. Yes.
We put p's power in the middle. It's not a metric anymore, right?
So as long as p is greater than or equal to 1, if I take this quantity, I take the pth root,
Yep.
then
But I mean,
that is a
the integrand, like say x minus y to the p's power, is
Yes.
not a metric anymore or distance anymore. If you take p as
But the
one.
pth root of that value is, because it's just the two metric. Maybe we'll defer on that and come back. For now, it actually won't matter a whole lot if this is really a metric. It's just a computation. Okay. So I've maybe convinced you that this is an interesting setup. What's the downside? Well, if we start with KL divergences, L1, L2 distances, there's just a formula for computing these things.
L2 is L2? Does that 2 need L2?
Yes, this is the L2 distance to the pth power. But what do we have here? How do we compute the Wasserstein distance? Well, it's not so easy. In particular, if I try to discretize this in the typical fashion, here I have a variable Tij, it's the amount of stuff I pick up at I, drop off at j. Well, and I have a linear program, right, where you can kind of squint at this and see how it's similar to the definition on the previous slide. So KL divergence is a formula. I can just type it into my computer and evaluate it. This thing is a large-scale linear program that scales quadratically in the size of my domain. In fact, moreover, if you're really sneaky and you kind of eyeball this, you might say, yeah, but the dual of this problem has a linear number of unknowns. That's absolutely true. However, as input to even specifying my linear program, I have this quadratic number of distance values, which is a big dense matrix. I can't even store it. So actually, my background, I kind of ended up in a faculty position in applied math in a funny way. I used to work at Animation Studio, and in that world, we have models that look like this. And even this kind of innocent teddy bear is comprised of, I think, 10,000 vertices. So this would be like a 10,000 by 10,000 matrix. And so only recently have there been algorithms out there for evaluating, computing these transport distances. And now finally, we can use them in some interesting applications. Now there's an additional interesting observation in this literature, which is something that we're going to kind of dig into today, which is that although I gave you one particular way to write down the transport distance, we'll see that there's actually many different interpretations. Right? So what I showed you so far is sort of a linear program. We'll see that there's a partial differential equation sitting here. This is the Monge-Ampere equation. You can actually interpret it as a geodesic distance in an infinite dimensional space of probability distributions. And there's even sort of a fluid dynamical interpretation of what's going on in this problem. And these are all the same in theory. They all give you exactly the same value, although the equations look very different. But in practice, they lead to very different algorithms, right? The ways that we discretize linear programs are quite different from the ways that we solve fluid dynamical problems. And so there's some really interesting questions hiding here. These are objects that are the same in theory, but different in practice. Now, on the one hand, this can be frustrating, right? You have two different algorithms that just look super different for computing transport. They have different approximation properties and so on. I would argue that this is somehow actually liberating. You have a choice, given an application of transport, to choose the right theoretical formulation of the problem and the right numerical technique for solving it in practice. And that this is an engineering decision, and that different techniques will have different properties that are useful in different places. And in fact, this is a theme that's well known in the computational world. Right? So there are many, for example, no free lunch theorems out there that sort of tell you that, you know, there's some well-known ones for the Laplace operator, for example, that say, if, you know, the Laplace operator has a bunch of properties in theory, right? It's positive definite and local and so on, has a maximum principle. And that any discretization of this necessarily must give up at least one of those properties. And I suspect that a similar thing is going on here, that actually the different formulations of transport, once we write them in a discrete fashion, have different properties, that much we know, but that's somehow built into the problem, that you must choose a discretization that makes sense for the application that you care about. So today, I thought I would outline three very different formulations of this transport problem that we've looked at, or maybe two, and then I'll run out of time, that's fine too. And kind of show you what it takes to take these theoretical ideas and translate them into a practical technique. So we'll first talk about some regularized techniques where you just want to extract an approximation of this value very quickly. These are, I think, sort of the best known computational techniques in transport right now, because there's a certain nerds paper a couple years ago that really brought back a lot of interest in this area. Then we'll talk about sort of a statistical version of this problem involving sampling. So what if I only have sample access to row 0 and row 1? I should have a black box that can draw one sample at a time. And then can I still compute these distances in a way where the expectation of that value is the one that I hope for? And then finally, we'll change gears completely and talk about a fluid dynamical version of the problem and what it takes to use methods like finite elements to solve these kinds of problems on domains that people computer graph. And then finally, if we have some time, I can highlight some other kind of fun projects that we've done in different applications. For instance, in a couple of weeks, I had a student presenting. He managed to take some of these methods and put them into a piece of DJ equipment for audio, which was a surprise to me. But it's been kind of a fun extension. Okay, so let's get started. So one thing to know about these transport problems is that they're often useful, but that doesn't mean that God told you that optimal transport is precisely the right model for a problem. It's just a model. right? Is in a useful distance, just the same as scale and so on, are useful in many applications, but maybe are not somehow the natural statistical thing. Sometimes they are, but often they're not. And so in that case, oftentimes it suffices to have an approximation of the solution to the problem that I sketched out for you, rather than really putting that additional computational effort into extracting a very precise answer. And there are many different reasons why you might want to do that. So for instance, in computer graphics, if we're coming up with ways to interpolate between different 3D models, clearly optimal transport may be useful for that, but there's no reason why we have to use precisely that model. In a machine learning, we often have just empirical and noisy access to our data. So spending a huge amount of computational time to evaluate these distances is probably not the #1 source of error that we have in a pipeline in that regime. So in that area, there's a very popular set of tools known as entropy-regularized optimal transport. These were sort of brought back to life by Marco Cattori in 2013 at the NIPS conference, and then we have some additional work together to show how you can do this extremely efficiently on large-scale domains, so long as they have some nice geometric structure. And the basic idea in this area is I take my transport problem, notice that's sort of the first term here, and I add to it a second term, which is measuring the entropy of my transport plane. Remember that entropy is a measure of disorder, whatever that means, or roughly just a measure of fuzziness, right? And so if I want my fuzziness to be large, I put a minus in front of that term. And here I visualize what this looks like. So here I have two one-dimensional probability distributions, and I'm showing the two-dimensional matching between them. When I solve this linear program with gamma equals 0, it's like the original problem. What I get is that the transport plan occupies a very thin slice of the product of these two measures. And that's actually sort of predicted by theory. Now, what happens as I increase the entropy is that some structure is preserved in my solution, but it becomes approximate. You can see that it becomes more and more blurry on the right-hand side. This is going to be an interesting computational trade-off, which is that this problem is hard. These problems become easier as I move to the right, but I don't get the value that I wanted. I get an approximation. In fact, one thing you can show is that when gamma goes to infinity, the solution to the transport becomes boring. It becomes the product of the two measures, just like a conditionally independent product distribution. So the basic observation in this literature, I'm going to skip over a lot of it because it's sort of old news at this point. So you can think of this transport problem as a convex problem with two big constraints. Right? One of them is that the integral over x is prescribed over y. The other is that the integral over y is prescribed over x. And so the basic observation in entropy regularized transport, actually connecting to the previous talk here, is that secretly, this objective, if you just do a little bit of algebra on your scrap paper, is the KL divergence between pi and a kernel, which is e to the minus distance squared. Yes?
Could you explain a bit what is the graph?
This thing here. Sure. So we have two different one-dimensional probability distributions. I've taken one and plotted it here, the other rotated it 90 degrees. And then the color here is the function pi of xy that I get when I solve the transport problem. Black means pi is large, white means it's small. So the way I should read this is that I pick up snow here, and I map it there. Right, so one thing you can show is that this is actually exactly the same, if I can just write it, as KL kernel of a particular kernel for k y equal to e to the So really what's going on is that there's some projection problem. That what I'm trying to do is to minimize, as we heard in the previous talk, some notion of distance between pi and a fixed kernel, but the fixed kernel doesn't satisfy these two constraints. Okay? And so these fast algorithms are essentially what they do is some version of alternating projection in this KL metric, where it projects just onto this constraint, and that one back and forth, and you can prove that this converges. And in fact, it's extremely easy to implement. What you do is you just take k, we scale the rows, and then we scale the columns, the rows, the columns, and so on. One thing to notice is that this kernel is nothing more than a Gaussian distribution. And so when multiplying by k, it corresponds to convolving against Gaussian, which is something we know how to do really, really quickly in the computer graphics world. which is the reason why we can solve these problems at extremely large scale very efficiently. So as some examples, here we have 4 different probability distributions, and what I'm showing is the interpolant that you get when you solve these transport problems. You can see that somehow the structure is smoothly interpolating from one shape to the other. On the other hand, you can also see what you pay by using these techniques, right? The solution to the transport problem is typically sharp, right? It's not a fuzzy object. But by adding entropy to our problem, we get kind of blurry edges to the shapes that we're interpolating. I would argue in computer graphics applications it's often acceptable because we're pretty good at sharpening images for the internet. Okay, so just recently we proposed a very different application of the same machinery in representation learning. For those of you who are not familiar with representation learning, the idea is that, not unlike metric learning, we have data which is in some strange modality, maybe it's images, maybe it's graphs, or what have you. And what I'd like is to learn a function from this hard-to-process modality into something, a space where I can do computations more easily. Right, so a very typical thing is to just map it into vectors in Rn, which you've probably seen, a deep network, that's a job in life. But there's no reason why the target of your embedding has to be Euclidean. In fact, there are a lot of drawbacks. There's a lot of theorems that say that certain spaces embed very poorly into Euclidean space, no matter how big it is. And so in this work, what we proposed was to use as a target for your representation learning problem, Wasserstein space in optimal transport, which specifically is just the space of clouds of points in Rn equipped with that particular metric. And of course, this is a fuzzy problem, right? I mean, this is a very heuristic thing that we're doing here. And so introducing entropic regularization is a completely reasonable sort of next step. And in fact, theoretically, one thing you can show just by borrowing some results from sort of metric theory is that there are many spaces that embed well into WP that do not embed well into Euclidean space. Okay, so we have many experiments in this research paper. As usual, I'm talking too much, and one of the interesting things is you can sort of do an apples to apples comparison here. The way that I do it is that I can take my data and I can map it into, let's say, 10-dimensional space, or I can map it into pairs of points in R5, right? So 2 points in 5-dimensional space. I shouldn't have chosen 10. Let's say 16. So I can do 1 point in R to the 16, 2 points in R8, 4 points in R4, and so on. Right? And when I have, say, 4 points in R4, I can take that space and equip it with the optimal transport metric, right? By thinking of probability distributions, measures that have 4 points of support. One of the interesting things we can show is that actually some of these embedding tools are more successful with the same amount of storage capacity by just giving a new metric to that same amount of values. And there's actually a different sort of useful takeaway, which is, let's say that I have a deep network and it embeds my space into 128-dimensional Euclidean space. There's a big problem, which is that at least I really struggle to visualize 128-dimensional space. But it's not so difficult to visualize 64 points on the plane, right? And so one thing that we can do is interpret those vectors in R to the 128 as a set of 64 points equipped with the transport metric, and that allows you to actually visualize the embedding that comes out of the metric tool that you're using. So for instance, here we did sort of one of these standard word-to-vec embedding problems. So you take a bunch of words in the dictionary, and your job is to embed them in a metric space where nearby words correspond to things that co-occur in the core thread of text. And then one of the nice things is that we find that it's actually quite useful for debugging your deep network, which is of course a very challenging task, because you can actually just look at what it's learning instead of having to use MDS or some tool like that to project. So for instance, here in the bottom, one of the things that we found is the word nice. Like there's nice, not nice, angry, like kind of feeling words. Often was embedded poorly using this tool. And after debugging a bit, one thing you can see is that nice, Paris, and France get embedded with very similar embeddings. These are the distributions. And the reason, of course, is that we were using a data set of travel text, and Nice is a city inference, and so that was good. Okay.
So, sorry.
Yes.
So you can use like this kind of idea to identify the possible meaning of a word.
Exactly. Meaning is a little strong. I know that people in natural language fight over that, but you can at least try to sense what words are close to each other. Yeah. Right. So now let's change gears and talk about a completely different approach to transport, and that's sort of closer to the statistical.
By the way, I don't quite get it. How is that related to optimal transport, the previous one?
So we're trying to solve a problem that says I have some distance metric on a very complicated space, and I'm trying to learn a map from that space into the space of point clouds, which is just a space of probability distributions restricted to a finite number of points, equipped with the transport metric.
Yeah, how does your figure show that differ from the standard word-to-vec type of?
The standard word-to-vec, I couldn't show you a figure like I see because I need a 128-dimensional projection.
But then what are you projecting here? What are you showing here?
Sure. So the idea here is that we restrict to probability distributions in the form. So probability distribution, which is composed of k points, where these points are all in the plane. Right? And so it's a smaller space of distributions, but one that we can actually visualize. Okay. So now let's change gears and talk about a completely different approach to these sorts of problems, sort of suited to statistical problems. The inspiration here comes from tasks where I'm trying to summarize data from multiple sources. It's not so hard to identify places where this happens. Like maybe I'm driving a vehicle and it has different sensors attached to different parts of the vehicle. These sensors are all sensing the same world in front of the car, but of course they all have slight bias because they're placed in different locations. Okay? Or a different setting where the same scenario occurs is in subset posterior methods in Bayesian inference. So if you don't know what that means, let's say that I have an extremely large data set. It's so large that my inference procedure fails. I don't have the computational resources to do Bayesian inference. Instead, I take my data set and I randomly IID divide it into 10 pieces, and I do 10 different instances of Bayesian inference on 10 machines. Now when I do that, each of the 10 machines gets a slightly different posterior distribution because they all have slightly different data. And so in the subset posterior problem, the question is, can I take those 10 inferred distributions and fuse them back together into one covariant signal? This is sort of a similar setting. Now, Wasserstein distances turn out to be extremely useful for these sorts of tasks. In particular, one thing I can do is solve for some notion of the average of multiple probability distributions in this funny geometry that I put on this space. And when I do that, a really beautiful thing happens. So here, let's say that I have 3 Gaussian distributions. That's what I'm showing you here. If I take this sort of classical average, so I just add them together and divide by 3, and what do I get? I get a probability distribution that looks like what we see on the left-hand side. That's not that surprising. What's more surprising is that if I take the average in Wasserstein space, what I get is a single distribution that's peaked at the sort of center of the 3. Right? This has to do with the fact that, again, the goal in life of optimal transport is to take geometry, in this case of the underlying plane, and lift it to a geometry on the space of distributions. And so you can see why this can be useful for these fusion tasks, right? So like these might be 3 different slightly biased probability distributions because I divided up my data. When I fuse them together, I don't just want something with higher entropy. I'd like to actually sort of merge the posterior. Okay, so our useful task, our useful technique here is going to be to use a technique called semi-discrete transport. And David is familiar with these sorts of tools. And the basic observation here is that let's say that I have 2 probability distributions and I want to measure their transport distance. And one of my distributions is composed of a finite number of points. The other one I can't say anything about. Maybe it's smooth, maybe it's not. We don't know. Now, initially, it looks like this optimization problem is infinite dimensional, right? I need a source point for every one of these blue points in that Wasserstein problem. But it turns out not to be the case. A very simple argument in one dimension, which says, let's say that I have a target for all the mass in this red arrow. And I have targets for all the mass in the second red arrow. One thing you can convince yourself is that there's never a case where they leapfrog like that. Make sense? So like, if the mass of the red arrow goes here, there's no case where the second one will go to its left. What that means is that secretly hiding here is a finite set of variables. There's an interval where the first arrow goes, followed by an interval where the second arrow goes, followed by an interval where the third arrow goes, and so on. So really, the only variables I have are the positions of the blue lines. Hopefully that makes sense. So in one dimension, the argument is straightforward. It's just a few lines. In higher dimensions, the diagram is much more complicated looking, but the analogy is basically the same, that there's some generalized notion of sort of a Voronoi diagram, called the Laguerre diagram, because you need control over the size of the cells. But the basic point here is that when you solve the transport problem and one of your two distributions is finite, this is actually a problem that's solvable, even though it kind of looks like you need an infinite number of variables. So building on that basic observation, my students and I worked on some problems that are sort of closer to the Bayesian style machine learning world, which says, okay, the transport problem I've given you so far, I mean, I keep using words like probability measure, but the variable is a matching between every point in the source measure and every point in the target, right? So it's not very probabilistic in nature. I need access to the entire probability distribution rather than just samples. So the question that we were trying to ask here was, let's say that I only have a black box that can draw a sample from row 0 and row 1. Can I come up with a procedure that's guaranteed to give a good approximation of the transport distance between these two objects in sort of an expected fashion? And now it's randomized. In fact, there's a derived question related to that fusion problem I gave you before. So here I've shown you the sort of definition of what it means to average in Wasserstein space. And so we have row 0 and row 1. So the average is somehow the thing that's at the midpoint, so it's those two things. The question is, if I have a procedure for sampling from row 0, and I have a procedure for sampling from row 1, can I come up with a procedure for sampling from the Barycenter? And that's what you would need in order to apply these tools to sort of inference tasks. So this is still, to my knowledge, an open problem in general. And so we have sort of an interesting piece of progress, which is sort of a funny halfway point that says, if I have a piece of machinery for sampling from these two distributions, we can come up with a way to approximate the middle distribution using a finite sort of prescribed number of points. It's not quite the same thing as sampling from the Barycenter. So here's a basic setup here. So if we'd like to approximate that measure with a distribution of this form, where these points are the unknowns. As usual, I'm talking too much, so maybe I'll defer on the details of the algorithm. The basic point is that there's sort of two sets of variables. One has to do with how you solve the transport problem, like the weights in your Laguerre diagram. The other set of variables is obviously the points that I'm moving around. And so there's a very simple alternating optimization algorithm, which has been well known in the computational geometry community for quite some time, but that you can adapt to the stochastic area by kind of noticing that the gradients here are all sort of expectations that you can compute by sampling, which is kind of nice. So the end result is a technique with many different applications. So for instance, maybe I want to find in the one distribution case, maybe I want to find the closest approximation of a smooth distribution with a finite set of points. One thing you might know is that if I do that by sampling, I don't get a particularly useful set of points. It's sort of a well-known brain teaser in the probability world. So instead, if I globally optimize over my set of points and say I'd like this empirical distribution to be as close as possible to the smooth distribution in transport distance, we can actually solve that in a fairly efficient fashion, and then what you get back is sort of the behavior you expect. So this is useful in certain probabilistic circumstances. Interestingly, it's also useful in printing. So if you have a black and white printer and you have a grayscale image, this is a very typical kind of task.
So the target distribution is smooth.
Exactly.
So what do you need? Do you need exact evaluation, or you need only?
No, but that's the trick. Is the only thing we need is to be able to draw samples from the smooth distribution.
From the smooth.
Yeah. Right. So for a very different application, actually drawn from sort of the classical machine learning world, Many of you may be familiar with the support vector machine, everybody's favorite piece of machinery for classification circa 2002. So in the support vector machine, we have a bunch of points. Some of them are maybe labeled with plus, minuses, right? Maybe these are cats, these are dogs. And my job is to train a classifier that separates them. In the support vector machine area, something really weird happens. You can prove a little theorem here. And it tells you that the separating hyperplane, that is the plane that sort of separates the blue points from the green points, actually only depends on a few points. These are called the support vectors. That's right. Now, what does that mean? That means that I could have removed all the points except for these three, and I would actually get exactly the same separating hyperplane. A little bit fishy, right? Because solving the SVM problem is a large-scale kind of complex optimization problem. There's a lot of people that study it and know how to do it pretty quickly. But so there's two basic observations I want to point out. One is that only a very sparse piece of your data set actually mattered for solving. It's the very classical, simple version of SVM. The second is that these data points are noisy anyway, right? So somehow these are just samples from some underlying distributional object. So somehow this suggests that maybe there's hope here in computational, right? That the typical algorithms for SVM scale in the number of data points, but most of these data points are garbage at the end of the day. However, there's a sort of a chicken and egg problem, right? I could throw away most of my data set if I knew which 3 points were valuable, but how do I know which 3 points are valuable? I solve the SVM problem, right? And that's the basic issue here. And so in the computational geometry, and more recently in statistical literature, they've defined an object called a Coreset. And a Coreset is sort of a conservative way to subsample your data. So the idea is that maybe I can't throw away most of the points here, but maybe these really extreme points I can convince myself really don't matter for my machine learning task. And so I can remove those. And so a Coreset algorithm, its job is to subsample my data set with a performance guarantee on what comes up. So in other words, I know that my SVM won't degrade that much when I remove these points from my data. So one of the kind of funny, unexpected applications of this approximation and transport distance work that we're doing is that it's actually relevant to computing Coresets. So one thing you can do is you can squint at the definition of the Coreset and actually write it in probabilistic language quite easily. By the way, historically, Coresets come from computational geometry community, so the notation is quite different. But really, one way to understand it is that it sort of fits nicely into the empirical loss setup that we have in the machine learning model. Where a Coreset is somehow, you have your loss function for your machine learning problem. You have one distribution mu, which is your actual data distribution. A Coreset nu, which is your approximation, probably on a finite number of points. And you like that somehow the performance measured by loss is not limited. So once you generalize this notion just slightly, one thing you can prove is that being close in transport distance, or in a different distance called MMD, not quite distance, is actually a sufficient condition for being a Coreset. It allows you to do two things. One thing is take our old technique for approximating things in transport, and it turns out that secretly we're computing Coresets, which is kind of nice. The second thing it does is it allows your Coreset to be things like mixtures of Gaussians. So rather than approximating your data set, which is a subsample, maybe I take a big data set, piece of my data set, and replace it with like the Gaussian distribution, which could be quite a bit of savings. It's sort of a different notion of the Coreset in practice. As usual, I'm low on time, so maybe I'll skip the other application I had of this sample-based transport. One kind of interesting thing that appears in Bayesian inference in the unsupervised setting. Like, let's say I'm trying to infer a mixture of two Gaussians, and then what I get is a distribution over two means and two covariances. There's a problem, which is mean number 1 and mean number 2 are indistinguishable, since if I swapped their label, I would have the same probability. So for certain inference procedures, that's a big problem, because I have a distribution with two webs, and a group that acts on that distribution, preserving probability. It turns out you can prove kind of a nice property of transport distance, which is that if I take the barycenter of a bunch of orbits of points under the action of a group, that's what I get as output, which means that secretly I can use these tools for inference and extracting points. In any event, in the last 2 minutes I have here, maybe I'll sketch out one final application, just because it's completely different from the other two, which is in the dynamical. So in this setup, The typical setup is sort of drawn from computer graphics, where now I have some domain, a triangulated surface. I have two signals on this domain, like the yellow color here. My job is to interpolate from one to the other. I'm going to do it in this particular case, but there are many cases in computer graphics where interpolation is really the key task. Okay? So there's a really beautiful, completely different interpretation of the transport distance, which is due to Benjamin-Brenier in 2000, which says that we can interpret these distances as sort of the path of the concentration of a gas as in a unit of time. In particular, look back at this slide, I'm going to think of the yellow color here as the density of the gas. So here it's high density, and here's low density. And I'm going to think of my interpolant as the gas moving around for 1 unit of time. And the sort of beautiful result from Benjamin-Brenier is that they showed that optimizing W2, finding the 2 Wasserstein distance, is precisely finding the animation of my gas displacing itself in 1 unit of time that minimizes this particular objective function. So here, mu is the density of the gas as a function of time. M is a vector field. This is probably kind of an unfamiliar notation, but let's say that I write the following. I think of my vector field M as mu times the different vector field V, and it's like change variables. Then one thing you can notice, if you look at the optimization objective function here, so this is 1/2 mu V squared, which you might recognize as kinetic energy. So this is the beautiful result from Benjamin-Brenier, which is that W2 is exactly the minimum amount of kinetic energy it takes to transform a gas from one pose into another. And so based on that observation, what we worked on was sort of a structure-preserving discretization of this kind of a problem on a triangulated surface. So in other words, if what I want is a way to solve this on a triangle mesh, but still having a convex problem and a triangle inequality, it's a little bit tricky because we're trying to solve PDE, where we have a discrete set of variables. It turns out that you can do that if you're extremely careful about how you set up your problem and find problems. The basic takeaway is that this interpolant has much better behavior than that entropy method that I showed you before. One kind of funny empirical observation about entropy is it actually messes with the velocity of your fluid as it moves along the surface. This is actually an unknown, theoretically, as far as I know, which is that if I add an entropic regularizer, empirically what people have noticed is that what tends to happen is the distribution sort of stays close to the first pose, then very quickly moves to the second pose at about t equals 1/2, and then stays at the second one. Whereas if you use this sort of geodesic technique at nice constant speed, this appears in many different examples. You can go holes, different topologies, and so on. And we can apply it to P and so on. But in any event, I think I'm out of time, so maybe we'll skip over our different applications, and it's my pleasure to share these slides later if you want to see some pointers to take the literature. But hopefully the takeaway that you have here is that even though there's really one transport distance in theory, there's many different ways to make it work in practice, and that these are sort of coupled with the different applications. Right? The sampling-based Bayesian inference requires a very different procedure for optimal transport than fast approximate computing in computer graphics or solving a partial differential equation in fluid simulation. And that by kind of pairing your numerical technique with your application, that's where you can get the increase in speed. So with that, I'm happy to answer any questions you might have, or I don't want to get in the way of your coffee break, which I know is outside, so I'm happy to hang out for the rest of the morning. So thank you very much for your time.
In the second part of the talk, you mentioned that we can approximate the continuous distribution versus discrete distribution. Right?
Mm-hmm.
So for that problem, if the target distribution is really high dimension, so is in that case the computation is still efficient?
The short answer is no. Yeah, so this is a fabulous question. So the question was, how does this scale with dimensionality? You might notice that most of the examples I showed here are 2 and 3 dimensional. So in optimal transport, there's a few theoretical results that we're doing. So asymptotically, you can ask the question of how many, so I have a smooth distribution over Rn, say, and then I have a budget of k points. right? And I have an empirical distribution here. And the question is how, if I compute the best approximation in this form of a smooth function, how does that converge this function of k and dimensionality? And so there's a lot of theory out there that talks about that. The basic issue is that as a function of dimensionality, there's an exponent that isn't terribly favorable. However, my colleague Philippe Rigolet at MIT, as a statistician, has some results that sort of tell you that what matters is actually the local structure of every of these distributions. It turns out that they're actually more or less concentrated on some lower dimensional manifold in a higher dimensional space than the convergences is. But it's a great question, and it's I would say probably the Achilles heel of applying such things to these
For the problem finding the middle distribution, it's an open question instead. But I wonder how would like gradient descent would perform such a question. You first take the naive average and the perturb and move to the direction which divides the sum of their respective distances.
So that's roughly actually what's going on in the ICML paper that I talked to about. But the problem is slightly different when it's open. So the problem that we worked on was, given sample access to two distributions, construct an approximation of that barycenter, that average, with a budget of k points. And there, gradient descent is quite effective. That's actually what I was sort of showing. The open problem is, given sample access to these two distributions, can I construct a technique that gives me sample access to the barycenter? Because at the end of the day, if I construct a barycenter like this, and I sample from it, I'll only ever get one of k points. Right? So it's not really a sample barycenter. Just an approximation. It's a little bit, there's some semantic issues there, but that's the basic issue. I do think that you can use a technique like this, draw one sample, and then throw the whole thing and get OA and then A, and that'll probably be some reasonable sample, but it's very hard to prove because it's a non-context.
So for the major Coreset case, so you use like as well as you use trivial example to for the major Coreset, the Coreset
Constant.
Coreset.
Oh, Coreset. I'm sorry.
Yeah, Coreset for you generate to any major, right?
Mm-hmm.
But use as well like as a motivating example. So I know there are some previous work I say. So you're like some Coreset work on the approximate, right? So how does like I mean, of course your method no general, right? So is that a clear case? So what kind of benefit you can extract from that?
Sure. Yeah. So right. I mean, there's a lot of work on Coresets. There's sort of two challenges. One is that typically the course, not all, but most Coreset papers apply to one learning task. Right? So let's say like here's a Coreset technique for vectorization, or here's a Coreset technique for k-means. The point here is that if I have a Lipschitz objective function for a learning task, then being close to W1 necessarily is a Coreset. Or if I have something that's in a particular Sobolev space, then being close to W2 is a Coreset. So it's a very general statement. The second part of this, the reason why it's a little bit useful, is that typically Coresets are just subsamples of your data. Right? So I have big data set, and I just want to throw away data in a fashion that preserves the performance of my learning algorithm. Here, we don't just have to throw away data, we can actually take big pieces of our data and like replace it with a parameterized distribution like a Gaussian. Right? So for instance, in that SVM example, if I could roughly take lots of positive examples and put one Gaussian on top of those, while the negative examples put another Gaussian on top of those, there's far fewer parameters, but it's still kind of summarizing a big piece of my data set. So it enables a much wider class of sort of representations for the course.
So what's the like the computational cost to calculate that?
Right. So not super high, right? So for instance, the technique that you were asking about before, let's say ICML paper, would be one way to compute this object. For mixtures of Gaussians, we show in our paper the fashion for doing it. I think computational costs, we have experiments, but nothing theoretical. It's sort of guaranteed question.
So I have a question about the way that you define WP. You use the P power of L2, right? What happens if you use LP you want to define WP? I mean, because I saw that definition as well. So
sure, yeah. Nothing really critical changes. The reason, okay, so anytime your cost for the transport problem has a triangle inequality, then that's like sort of the main thing ingredient that you need for it to work out. We typically use L2 because that's the ones that we care about a lot of the applications. There's one beautiful case, which is the L2 distance with P equals 2, which is what enables this kind of fluid dynamical manifold interpretation. And that's very specific to the number 2 because you need an inner product. So yeah, there's a really nice, actually two really nice textbook by Eulerian that are sort of outline all of the theory that is a concern.
You mentioned some spaces embed poorly into Rn. So how about test space, or in particular worst space? Worst space?
The worst space.
Worst to, you know,
Oh, the worst space.
The worst space.
Yeah,
Oh,
I don't think
yeah,
anything is known theoretically. Yeah, empirically we found that it embeds better into Wasserstein than into Euclidean space. Of course, the trade-off being that the computational cost is much higher. Yeah, I don't know. I mean, you would have, I think theorizing about embedding words is a tricky matter. Yeah, I'm actually not sure what the results are. It's a good question.
So if we embed it into the WP, so how, could you imagine how about the results?
Yeah, so empirically, for the same budget of bits on your computer, embedding into WP, we found the distortion amount was lower. In other words, the distances were better preserved. That's an empirical result. I think theoretically it would be quite hard to say something. A case where there might be some hope for saying something theoretical is that there are people who work on embedding graphs into different spaces. So for instance, it's very well known that trees embed well into hyperbolic space. What we found empirically was actually kind of, there's some experiments in that paper you should take a look at. It's kind of cool. We took different probability distributions over graphs, like conditional and some distributions over trees, and then used this embedding tool. What we found is that typically this was a stronger embedding than hyperbolic or Euclidean space, except when your graph is a tree, and then the hyperbolic one is. So somehow it aligns with the theoretical prediction, which is nice. Yeah. Certainly that piece of research is extremely empirical. Yeah.
No more questions? Let's just a bit. Coffee time.
Oh,